All right, so this Physics 12 lesson is going to continue with our work on circuits. So in our previous lesson, we talked about just some basic circuits and the use of Ohm's law being a connection between voltage, current, and resistance. Okay, and what we're going to be looking at today is, again, there's some differences between parallel and series circuits, and then a few things called Kirchhoff's laws, which enable us to use a kind of a combination of Kirchhoff's laws and Ohm's law to be able to calculate information about different current, voltage, and resistance at various points in either parallel circuits or series circuits or a combination of both. Okay, so that's what we're going to be getting into today. All right, so just as a quick review, I don't know how much of you remember this from maybe junior high science when hopefully circuits in some capacity were demonstrated to you, but when we do talk about circuits, okay, we've got some key points that we want to be able to demonstrate, and you're going to see a lot of diagrams in any sort of practice questions and worksheets, and you need to know what each of those diagrams, what each of those parts look like in the diagram. So in a circuit, what you'll see is a battery represented by these combination of long and short lines. The longer line represents the positive terminal end of the battery, and the shorter line represents the negative terminal end. Okay, so since our current is always going to flow from high potential to low potential, current will flow this way around the circuit. Okay, and again, we know that that's opposite to the way that the electrons are flowing, but this is the conventional way that we draw current, right? Going from high potential to low potential. Resistors, which could be, you know, it could just be just a basic resistor, but anything that would put resistance, so whether it's a motor or whether it's a speaker or it's a light bulb, those would all be examples of objects that would give resistance to current within a circuit. Sometimes they will have special symbols themselves for like a bulb or a motor or a speaker, but typically what we just see is that there's some sort of resistance happening and just kind of given by those little squiggles there, okay? So those are the big things you need to know when it comes to your diagrams. Everything else is just considered wire, okay? We'll get to some other examples and I'll mention those as we get there, okay? The other big thing we need to go over is just the difference between a parallel circuit and a series circuit, okay? So when we're talking about a series circuit or resistors being connected in series, right, this is here in this diagram, what that's showing is that they're all along the same path. Okay, so resistors that are connected in series are all along the same single path of current. So if we look at our battery here, and we talked about the flow of current, current would flow out through this positive terminal end, and it will pass through resistor 3, 2, and 1, and then back this way. And notice how there's only one path in this case for the current to go, okay? And these resistors are considered in series with each other because they are all part of the same path that the current would flow through. This is different to resistors that are connected in parallel, where there's different paths for the current to travel. Right, so here what you'll notice is that we have 3 different paths at which the current can go from positive to negative end of the terminals of the battery, right? So we can go here through resistor 1, or we can go here through resistor 2, or here through resistor 3, right? So they're resistors connected in parallel, meaning they're on different paths of the current, right, or different paths of the circuit flowing, okay? And this is where the big differences are going to come in terms of Ohm's law and Kirchhoff's laws about what happens with total resistance, what happens with total current, and total voltage, given the different types of circuits, okay? So in 1845, German physicist Gustav Kirchhoff developed a set of rules which deal with the conservation of current and energy within an electric circuit. So he described 2 important laws with respect to circuits, both of which relate closely to the law of conservation of charge. Okay, so we'll get into those. So we first have Kirchhoff's junction rule. And Kirchhoff's junction rule says that the sum of the currents into a junction is equal to the sum of the currents flowing out of the same junction. So mathematically speaking, current in is equal to current out. Right? So again, if we go back to just our diagram here, what that's showing us is that the current that's going to leave here, right, and there's only one path for it to go, is going to be the same as the current that comes out, right? So going into this junction here, right, is going to be the same as the current that comes out. In a parallel circuit, notice that there's different, right? If you think about current being like a river flowing, right, in this case, it's got one path and it's going to go through, and all the water is going to pass through that one little section. Whereas if we're thinking about it in a parallel circuit, if we're coming down and now all of a sudden we have choice where we can go through here, or we can go through here, or we can go through here, all of, the current, or if we think of it as like with the water example, the water might split up and go down different paths, but eventually all leads back out again. And that's still saying that the current in, right, the current that was here before it split off into the two different spots, right, at this junction, is still going to equal to the current out. So if this current splits into 3 different paths, by the time those 3 paths line up again due to the conservation of charge, we get the same current back out here again, okay? And you can also kind of think of, going back to that water flowing analogy, water's going to choose the path of least resistance. So depending on what the resistance is of the different resistors on each of the paths that are in parallel, you'll see more current potentially passing through the one with the lower resistance because it's easier to travel that direction. Some will still travel the other, but the spot where it's easier will work. Okay, so that's that kind of first junction rule. Okay, then we have Kirchhoff's loop or voltage rule, right? And that says for any closed loop, the sum of the voltage lifts is equal to the sum of the voltage drops. Okay, so what that's saying is that, whatever voltage was available here should all get used by the time you get to the end. Okay, so like coming across the battery is a voltage lift, right? So this, in a very simple circuit, when you cross the battery, that's an increase in potential energy. So you have an increase in voltage coming across the battery, and then as you cross the resistors, you drop, and drop, right? Until you're back down to 0. Okay, so again, this is a very simple one where there's just a single battery, but if there was ever a point where you came across another battery, like between 2 resistors, right? Again, the amount that you're going to increase going across that battery all together from doing an entire closed circuit, okay, the number of increases through going across the battery and the number of drops going through resistors need to end up being 0. Okay, so basically all of the voltage and potential energy is used to cover the battery by the time it finishes its circuit. Okay, now, as mentioned there, right, that junction rule that we just first talked about, that was related to the conservation of charge, and Kirchhoff's loop rule is related to the law of conservation of energy, right? So again, saying that everything here is going to be used shows that all energy is conserved, okay? So this then kind of brings us to this idea of total resistance, okay? And there's a difference here again about what's happening in whether you're in series or you're in parallel, okay? So if your resistors are connected in series, your total resistance is just the sum of all of those resistors, okay? And that's going to be the total resistance in that circuit. However, if your resistors have been connected in parallel, okay, it actually overall lowers the overall resistance of the circuit, because what you get is that you get the same amount of voltage being able to pass through each of these paths, right? And the current is split equally, right? So your total resistance is actually done by quite a different formula. So what it is that the total resistance here is like an inverse law, where total resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and then the inverse of that. So just switch to the board here, because do I have a better diagram? I don't. Not right now, anyway. I think it's later. But what that's saying here is that in a parallel circuit, right, your total resistance is actually going to come from an equation that looks like this. All right, so your total resistance is actually here in the denominator. Okay, so you would need the resistances of each of the other resistors in the parallel circuit, and you do the inverse of each of them, like 1 over plus 1 over plus the reciprocal, 1 over plus 1 over plus 1 over, and then that will all equal 1 over the total resistance, right? So ultimately, if you end up getting like that 1 over RT, just for example, ends up equaling to like 1 over 8 ohms, right? Then you know that your total resistance ends up equaling 8 ohms. Okay, so what you were seeing in that other slide was it written like this, where it was RT is equal to the 1 over R1 plus 1 over R2 plus 1 over R3, and then that all was to the -1, right, indicating with your laws of exponents that it's just flipped 1 over whatever that sum is, right, and that's what that's coming from there. But that equation might be a little bit easier to follow than that one that was in the slides, okay, but it's the same. Okay, so again, if your resistance is in series, right, if your resistors are connected in series, it's just adding them all up, it's the sum of them. But in parallel, you use the sum of the reciprocal for each measure of resistance, and then it's the reciprocal there to get the total. Okay, so again, just some extra notes there about, the total resistance in a series circuit, like I said, is the sum of all the resistors. So since each electron has to push through each resistor, it makes sense that those resistances are cumulative, right? Because the current only has one path to travel, it has to go through all of them, right? So the total resistance is it has to pass through each of them, okay? And then the inverse total, okay? The inverse of total resistance in a parallel circuit is the inverse of each resistance in that circuit, right? Because basically what's happening there, when your resistors are added up in parallel, your total resistance is decreasing. And just think about this a little bit logically again. All of your electrons are not being forced through the same path, okay? They have multiple paths to choose from because you're set up in parallel, all right? So because of that, the resistance overall is lowered because the current has a choice of basically which way it's going to go, okay? So if all electrons are forced at the same path, there's going to be more resistance, but if they have multiple paths, there's less resistance, right? So even if you think again about that analogy of like water flowing down a river or flowing down a mountain or something, right? If there's only one spot and you have to pass through a series of boulders and then you have to pass through a series of smaller rocks and you have to pass through a bunch of, plants and roots and trees and stuff, and you have to pass through all of them, and there's only one way to do that, right? That there's a large amount of resistance. However, if the river kind of branches off and one just has to pass through the boulders and one just has to pass through the series of roots and plants and one just has to pass through the smaller rocks, right, by the time they come together, overall less resistance was encountered. All right, so that's what's happening there. Okay, going back to voltage again, so for the series circuit, right, the total voltage increase across the battery has to equal the drop across each resistor, right? So if you can calculate the voltage drop in each resistor, that can tell you the total voltage that would have been across the battery, or if you knew the voltage across the battery and you can calculate the voltage drop through each resistor, right? Right, or you knew 2 of them and you can calculate the third, right? So basically the sum of all of those voltage drops in series will equal the total, okay? In parallel, again, it's different because the voltage in any part of the circuit is the same across all resistors. So the reason that is because the potential energy difference between 2 points in a circuit is the work done when 1 coulomb of charge passes between the points. So at each of the junctions, right, each of the paths of the parallel circuit, you have the same voltage available because you have the same potential energy to cross through each of those paths. So what that's saying is that each path in a parallel circuit has the same voltage but different values of current because the current is what's splitting off, okay? So one way to just kind of visualize this and keep all of your formulas straight, and this would be something you'd probably want to include in some, an important set of notes or something to have, if of all the slides in this one, this is the one you're going to want to have handy when calculating different parts about voltage, current, or resistance in different circuits, is that, again, we know that through Ohm's law, right, voltage is equal to the product of current multiplied by resistance, but now we need to be conscious of the fact of, is this particular circuit, is it a series circuit, is it a parallel circuit, and what does that mean for the total voltage, the total current, and the total resistance, right? And then also giving us information about little sections of it as well. So with voltage, right, in a series circuit, the total voltage is the sum of all the voltage drops, right, within each of the resistors. Whereas when you have resistors connected in parallel, the total voltage is the voltage going through each of the paths, right? It's the same value. With current in a series circuit, you only have one path for the current to flow, so the total current of the circuit is the current passing through every single one of the resistors. However, that's different when your circuit is set up in parallel because your total current is equal to the sum of all of the other paths, right? Now this is assuming, of course, that there's only 3 resistors, okay? But obviously there could be more or less. And then again, total resistance here is that the total resistance with a resistor is connected in series is the sum of all of the resistors, whereas when they're connected in parallel, it's that inverse, like the 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc. Okay, so this, like I said, this is going to be kind of your key formulas slide that you're going to need to use, and just really pay attention to that, because you see how similar they can be, right? Just depending on whether you're in series or parallel, right? I mean, like current versus voltage in series versus parallel, right? Those almost look the same. Same thing here, but they're swapped, right? So just be careful as we go through some of these problems. Okay, so now we get into our using of these laws, right? How do these formulas apply to different situations? How can they be helpful in finding different pieces of information? So this is where I also bring into learning, I guess, some more information about drawing circuit diagrams. So I'm just going to redraw this one again here. So like I mentioned, this symbol here is your battery. These are your resistors. And these circles with A, those are what we call ammeters, okay? Ammeters are devices that are used to measure current in a circuit. Okay, ammeters, you'll notice the way that they've been placed in this diagram here is that they're actually placed in series with the resistors, right? They're along the same path. So if you're trying to measure current within a circuit, a little bit almost dangerous because you have to pull it apart, right, and insert this device here. But an ammeter has to be connected in series, right, along the same path, right? And again, that makes sense because if we're trying to measure current, then it has to be in the path of the way that the electrons would actually be flowing or the current is flowing. Okay, so this is our diagram, right? What we have is that we've got clearly a 12-volt battery, right? Right, so there's 12 volts of potential energy coming from the battery. In this first resistor, we know that the resistance is 3.0 ohms, and we are interested in what is the value of the current flowing through this this resistor, right? What is the current at this point, right? If we had an ammeter connected here, what would be the current flowing through here? Down at the bottom, our second resistor has a resistance of 4 ohms, right? And again, we're interested in what is I2, right? What is the current flowing at that particular junction? And our third resistor has a resistance value of 2 ohms, and we're again interested in what is the current flowing there, right? So we're interested in what are the values of I2 or IT, I2, and I3, which would in this case also be I1, because we can see that this is in fact a series circuit. Okay, so as mentioned, since this is a series circuit, right, when you have a series circuit, that means that the current is the same at all points. So already we know that I1 is equal to I2, which is equal to I3, which is equal to the total current. Okay, so that is already kind of straightforward. So once we find one, we've found all of them. Okay, so if we think about the total current in this case, right, your total current can be found using Ohm's law, where your voltage is equal to current times resistance, or just current is equal to, so the total current is equal to the total voltage divided by the total resistance. Right, and we have values that we can get for each of these. Our total voltage here is 12 volts coming through the battery. And since our resistors are connected in series, our total current is just the sum of all of the resistors. So 3 plus 4 plus 2, which is 9 ohms. Right, so we can just do that division there, and 12 divided by 9 gives us 1.33. We only get 2 sig figs in this question, so 1.3 amps or amperes, and the sun has apparently decided to make this very tricky trying to see my board, but there you go, 1.3 amps would be the value. So again, because it's a series circuit, the current is the same everywhere, so our current at I1 is 1.3 amps, our current at I2 is also 1.3 amps, our current at I3 is 1.3 amps, and our total current, right, flowing through that circuit is also 1.3 amps. Okay, so there's the first example. Right, and again, you get that same explanation, right? There's your total resistance. It's a series circuit. All the currents are going to be the same, so your total current is total voltage divided by total resistance, so it's the same everywhere. Okay, let's take a look at sample problem number 2. I think the longest part of this video will just be waiting for me to have to redraw these diagrams on my whiteboard. Okay, so this one is kind of a combination, but we do have here a set of resistors in parallel, and then a second resistor that would kind of be considered in series because it has to, you have to pass through that one, right? So again, here's our battery. We're passing through an ammeter, so we know the current passing through this point is 2 amps. We would then pass through the first resistor and then pass through here, and then our current would split, some of it going here, some of it going here. More likely, more of it will go here, right, because there's less resistance. And then it would pass through and then come and complete the cycle. What we're being asked in this particular question is, what is the potential difference supplied by the power source in this circuit? Essentially, what's the voltage of the battery, right? So knowing that the total voltage drop would have to go down to 0 by the time it got back around, okay? So bear with me for a second while I just try and re-sketch this diagram. Where was the ammeter? Up there. Ammeter, resistor, break off into 2 little sections. Come back together, go in, go around. Okay, and we've got R1 has a value of 8 ohms, and R2 is here with a value of 12 ohms, and R3 is here with a value of 24 ohms. That is a terrible omega sign. There we go, we fixed it. All right, so here's where we're at. Okay, so this is what we're looking for. We are looking for, what is this total voltage? Okay, so one of the things that we can conclude, oh, and I forgot to write in that the current was measured at 2.0 amps. Okay, so we can look at things at different sections. So let's look at what's happening here at R1. Okay, what voltage drop has occurred here at R1? We know that the current is going to be 2 amps, right? Current in is going to have to equal current out. So coming through here, you're going to get 2 amps of current passing through an 8 ohm resistor. So we can figure out that voltage at 1 is equal to current 1 multiplied by resistance 1. So that's going to be 2 amps multiplied by 8 ohms. Right, so our first voltage is 16 volts, right? So we know that this battery has to be at least 16 volts because it's going to drop 16 volts just by passing through this resistor, okay? Now, at that point, okay, we then would split, right? We've got our parallel circuit here, right? And we know that whatever the voltage is across here, right, V2 is going to be the same as the voltage going through here, okay? So if we can figure out what's the drop, what's the voltage drop over here, okay, then the sum of those drops will equal our total voltage potential of the battery, okay? And it's going to be the same here, okay? So the voltage potential is the same in parallel circuits. It's just the current that's going to split, okay? So what we can figure out here is, well, right now we don't know how exactly the current's going to split, and we don't know what those values of V are going to be because we don't know the total. So what we actually need to take a look at here is, well, what's going to be the total resistance in this little section, right? In just the parallel section, what is the total resistance? So I'm going to label that as R sub P, right, the resistance in the parallel section of the circuit, okay? And since they're in parallel, I would do it as 1 over is equal to 1 over the resistance 2 plus 1 over resistance in 3. So 1 over RP is equal to 1 over 12 plus 1 over 24. And what you get there is 1/8. So 1 over RP is equal to 1/8. So that means that the total resistance in this little section here is 8 ohms. Okay, so in this parallel section of our circuit, the total resistance would be 8 ohms. And the total current in this little section is still going to be 2 amps, right? So we're thinking of this as like a whole, right? So as a whole, the total resistance is 8 ohms. As a whole, the total current, even though it would split into 2 separate sections, the total current would still equal 2 amps. So we can calculate what the voltage would have been, right? So like VT kind of thing for this section, or I'll call it VP for the parallel section, right? So the total voltage here in the parallel section is going to equal the current passing through the parallel section, right, total, and the total resistance of the parallel section, which is, again, 2.0 amps multiplied by 8 ohms, so it's another 16 volts, okay? So because of that, right, you get a potential drop of 16 volts here, and you get a potential drop of 16 volts in the parallel section, so our total voltage of the battery is 16 plus 16, and will be 32 volts. Okay, so that's that one. And then again, there's your solution, right? So in order to solve it, we needed the total resistance. We can't determine without the value of the net resistance coming from the parallel resistor, so that's why we broke that up there, right? Because that was in series, so we did that, calculated that the resistance from the parallel section is 8 ohms. Then we can see, this is another way you can do it as well, where you can look at the total resistance as a total of 16 ohms and the total current being 2 amps, so total of 32 volts, or we can do it in the sections how I showed you as well, right? So there's a couple different ways you can try and tackle it. Just make sure you're following those rules of Ohm's law and Kirchhoff's law, okay? So this will be our last problem that we'll do, right? Again, using these different combination of Ohm's law and Kirchhoff's laws. So in this one, given the circuit shown above, we're going to determine the following things. We're going to find V4, so what's the voltage at V4, right? Right, so what's the potential drop that's happened here? We're going to find the resistance at 3. What is the value of this resistance in ohms? We're going to find what is the current that's passing through this. So we know that the current coming out is 1.5 amps, but it passes through this section of parallel where the current would in fact split. So this is going to have to be something different, right? Less than 1.5 amps, right? And then our value, we're looking for the power, right? What power exists here at 1, and what's the total power given by this scenario. Okay, so once again, I'm just going to try and draw that diagram again so we have something to reference as we work through those problems. My resistors are not the best looking. Please forgive them. Okay, so we know that the voltage across the battery is 18 volts. We again see that that ammeter, they're measuring the current, right? So it has to be placed in series with resistors in order to measure current correctly. We have a value for R1 is 3 ohms. We have a value for R2 at 6 ohms. We don't know the value for R3, and we know that the resistance here at 4 is 5 ohms. Okay, so we are ready to go. Okay, so the first thing we're being asked to find is what is the voltage drop here at V4, okay? So really, what's happening though is at this point, our voltage is happening in series, right? So we know that the current's gonna be passing through a resistor that has a resistance of 5 ohms, and we know that since the way current's working, if it's current in equals current out, at this point we've already split and come back together, so it was 1.5 amps coming in, it's 1.5 amps coming out again, so we have the resistance here, we have the current here, it's going to be the 1.5 amps, so our voltage is just going to be found using Ohm's law, where we would take our current of 1.5 amps and multiply it by the resistance of 5 ohms and get that the voltage drop across that particular resistor is going to be 7.5 volts. Okay, so that one's relatively straightforward. Okay, in part B, what we've been asked to find is what is R3. Okay, so again, what we might want to consider here is, again, what's the total resistance here? Okay, so we can start by saying, well, using just basic Ohm's law, we know the total voltage of the entire circuit is 18 volts, and we also know that the total current is 1.5 amps. So our total resistance will just be a rearrangement of Ohm's law, which is the total voltage divided by the total current. So our total resistance is going to equal 18 volts divided by 1.5 amps, which is a value of 12 ohms. Okay? Now, in that 12 ohms, what you have is you have two resistors that are connected in series, which already give us a total of 3 and 5, which is 8, right? So our total is going to come from our first resistor plus the total resistance coming from the parallel section, so like R from the parallel section, plus R4. Okay, so we know that this 12 ohms is coming from 3 ohms plus resistance from the parallel section plus 5 ohms, which gives us the fact that we know that RP is going to equal a total of 4 ohms, okay? Because we're just subtracting 3 and subtracting 5 from 12. So 4 ohms is going to equal RP. And the resistance coming from the parallel section, we're going to have to find using that inverse section where 1 over RP is equal to 1 over 6 plus 1 over R3. So we actually know that RP is 4, so we can replace that here. So 1 over R3 will equal 1/4 minus 1/6, which is actually just 1/12. Okay? So if I kind of erase this section, it shows you that. Right? So 1/4 minus 1/6 is equal to 1 over R3. That's 1/12 is 1 over R3. So therefore we can conclude that the resistance on R3 is in fact 12 ohms. Okay, so now we know that this is a value of 12. All right, so next we are being asked about the current passing through I2. I think that was the right question. Let me just triple check. Yes, so what's the current passing through resistor 2? Okay, so give space to solve for that one. So this one's not as straightforward because at this point resistor 2 has been set up in parallel, so that 1.5 amps of current is going to get split. Okay, so what we do need to figure out though is how much it's going to get split by. So what we can figure out here though is what's the potential voltage drop first when it passes through R1, okay, and what's the potential drop as it passes through R4, right, and then we can figure out the other ones. So what you've got is V1 is going to equal 1.5 amps multiplied by 3 ohms, which is 4.5 volts, right? So you're going to get a drop of your 4.5 volts happening here. You can figure out the same here at V4, right? Which is again going to be 1.5 currents multiplied by 5 volts, which we actually solved for in part A, which was our 7.5 volts, okay? So what that means is what we have left, right? The potential voltage is the same here as it is here, right? So V2 is actually equal to V3, and we're interested in V2, so V2 is going to be 18 minus 4.5 minus 7.5. Right, because again, using Kirchhoff's law, we know that the voltage here is going to be the same as here, and the sum of this one this one and this one will equal 18. So it could either be 1 plus 2 plus 4 will equal 18, or it could be 1 plus 3 plus 4 would equal 18, because the voltage here and here on these same branches of the parallel circuit are the same. So that means the voltage going across number 2 is going to end up being 6 volts. When we do that math, right, 18 minus 4.5 minus 7.5, we get 6 volts. So now that we know that we've got 6 volts passing through here, and we know that the resistance is 6 ohms, we can calculate that the current passing through 2 is going to equal the voltage passing through 2 divided by the resistance at that junction 2, which is just 6 volts divided by 6 ohms, so our current is just 1 amp. Okay, so that's what's happening there. And then you could, if you wanted to, explore something similar here, knowing, okay, the voltage would have been the same at V3 as it was at V2 because these are in parallel. So your voltage here also would have been 6 volts, and the current passing through here would have been 6 volts divided by 12 ohms, which gives you 0.5 amps, and you'll notice that, again, the sum of 1 plus 0.5 amps ends up equaling your total current of 1.5 amps. Okay? So that was part C. Then part D was asking for about the power, so like the wattage that was happening here at the first junction. And if we go back to your lesson on Ohm's law and all the connections between Ohm's law, voltage, resistance, current, and then adding power into the fact, we had one of those equations that came out of that big circle was that power was equal to resistance times current squared. Okay, so we're interested in what's happening at this point here. So the power at junction 1 is equal to the resistance of 1 multiplied by the current at 1 squared. So that power is just going to be resistance, which is 3 ohms, multiplied by the current, which we know at that point is 1.5 amps, and we square it. So 3 times 1.5 squared gives us a value with 2 sig figs of 6.8 watts, all right, at that point. And then finally, what we're being asked is PT, so the total power in this situation. So once again, you can use that same idea here, right? And you could use your total resistance and your total current squared. Okay, the other thing you could do is, remember again with that circle, you had a bunch of different options for how you wanted to figure out power, right? The connections between them. So in that last part, you could also use a different version, which is that the total power is equal to the total current multiplied by the total voltage, right? And in that sense, we know that the total current is just 1.5 amps multiplied by the total voltage supplied by the battery, which is 18 volts. And when we do that, we get a value of 27 watts. Okay, so lots of things that can be found at different parts of a different circuit. Again, remembering that you have to use the correct rules for whether or not you're in series or whether or not you're in parallel, right, and seeing these combination circuits as well. So again, you've got a worksheet to look at. I've also uploaded a second video, right, so there's my video, and if you want a different person trying to explain it to you, I also have one from a different teacher that I found that's pretty good, a lot of physics teachers use, if you want to read through that. And then there's also, I think I'll post another crash course one if you're just wanting to kind of keep learning about, you know, just more and more stuff with circuits and just having explained in multiple different ways. So I'll post my video as well as the one from a different physics teacher that's maybe only 10 minutes long, and then another crash course. Don't feel like you have to watch those. This is sufficient to do your worksheets, but if you just feel as though maybe some other people can explain it better, by all means go through those videos as well.